Business quiz time. What does Bill Gates, Warren Buffett, and closer home, Lakshmi Mittal and the Ambanis have in common? Great vision, tremendous business sense. I have a friend Shiv, who's an aspiring businessman. He wants to set up a manufacturing unit in minimum time, incurring the least cost and generating maximum profit. Sounds like a fantasy? No, it's the formula for survival in the business world, where the rules are constantly changing. Whoever cracks these problems with their constraints is headed for fame and glory. But let me tell you, it's not simple. Figuring out your logistics is no cakewalk. Fortunately, my friend Shiv is in good company. Who else is it? It's me, Shankar, of course. And I'm going to help him draw up a good strategy using the principles of linear programming. Want to know how? Follow me into my studio. Well, they say you have to walk a mile in someone else's shoes to really know about their problems. So I decided to ask my friend Shiv to give me some concrete data such as this, so I can help him set up his business. Hey, welcome to Math with Shankar, where we help you solve your problems logically and magically with minimum time and maximum scores. Today, we will be looking at solving problems in the important field of optimization. The techniques we describe here are critical to business decision making. Well, time is money, so let's see what's on the agenda for today. In this episode, we will first revise the concepts of linear programming. Then we will tackle various problems on transportation and manufacturing and so on. And let's not forget, to get those top-of-the-line scores, we prepare you to meet the ultimate challenge with Exam Decoded. The best way to introduce you to this wonderful world of linear programming is to solve a bunch of problems. You don't have a problem with that, do you? To begin with, let's revise some key concepts associated with a linear programming or an LP problem. An LP problem is very simple to imagine. It has two parts. The first part is an objective function such as cost or profit, which has to be optimized. The second is a set of constraints like labor, materials, and so on. They are not unlimited usually. So let's give this a mathematically precise shape. In any optimization problem, there are a few things that can be varied under some constraints, of course. These could be hours of labor that he can afford, the amount of a chemical that he can use, and so on. These are called variables. For the moment, let's get back to my friend Shiv and his manufacturing unit. Shiv has decided he wants to manufacture photo frames. Photo frames like these, specially made for me, right? Well, I was just joking. Now his first task is to set up a factory. Now to set up a factory, he finds a nice piece of land conveniently located. Next, he gets in touch with a brick manufacturer and surprise, surprise, this guy too is solving his own problems using, you guessed it, linear programming. Let's see what his problem is. The brick manufacturer has two depots, A and B, with stocks of 30,000 and 20,000 bricks respectively. He receives orders from three builders P, Q and R for 15,000, 20,000 and 15,000 bricks. The costs in rupees of transporting 1,000 bricks to the builders from the depots are as shown in the table. So my question for you is, how should the manufacturer fulfill the orders so as to keep the cost of transportation down to a minimum? Well, let me help you with this one. We make a critical observation here. The total supply adds up to 50,000 bricks, which ends up as being the exact amount on demand. One key skill is to identify the variables of the problem. We have two depots here and bricks to transport from them. Let the depot A transport X1000 bricks to builder P and Y1000 bricks to builder Q. Now, since the depot A has a stock of 30,000 bricks, the remaining bricks amounting to 30 minus X plus Y1000 bricks will necessarily be transported to the builder R, since demand equals supply. Now remember, the number of bricks is always a non-negative real number. Therefore, we have three conditions: X greater than or equal to 0, Y greater than or equal to 0, and 30 minus X plus Y is greater than or equal to 0. Or more crisply put, X plus Y less than or equal to 30. This brings us to the requirement of 15,000 bricks by builder P. X1000 bricks are transported from the depot A. Therefore, the remaining 15 minus X1000 bricks are to be transported from the depot B. The requirement of builder Q is 20,000 bricks, of which Y1000 bricks are transported from depot A. Therefore, the remaining 20 minus Y1000 bricks are to be transported from depot B. Now, depot B has 20 minus 15 minus X plus 20 minus Y, or in other words, X plus Y minus 15,000 bricks, which are to be transported to the builder R. It follows that 15 minus X is greater than or equal to 0, 20 minus Y is greater than or equal to 0, and X plus Y minus 15 is greater than or equal to 0, giving us three conditions: X less than or equal to 15, Y less than or equal to 20, and X plus Y greater than or equal to 15. Having figured out amounts to transport, we move on to the associated costs. The transportation costs from depot A to builders P, Q and R are given by 40 times X, 20 times Y and 30 times 30 minus X minus Y, which are all given in hundreds of rupees, mind you. Careful about units. Similarly, the transportation cost from the depot B to the builders P, Q and R is given by 20 times 15 minus X, 60 times 20 minus Y and 40 times X plus Y minus 15. Therefore, the total transportation cost Z is given by Z is equal to 40X plus 20Y plus 30 times 30 minus X minus Y plus 20 times 15 minus X plus 60 times 20 minus Y plus 40 times X plus Y minus 15, which implies Z is equal to 30X minus 30Y plus 1800. Obviously, this cost has to be minimized as an objective. Therefore, the linear programming problem can be stated mathematically in this manner. Find the combination of X and Y which minimizes Z is equal to 30X minus 30Y plus 1800, subject to X plus Y less than or equal to 30, X less than or equal to 15, Y less than or equal to 20, X plus Y greater than or equal to 15, and X and Y are both non-negative. Once the linear programming problem is formulated, let's say that my friend Shiv can easily solve his problem. So Shiv takes the next step of placing the order. But hold on a second. My friend's problem doesn't end at bricks. There's more to business than setting it up, right? Transportation is a problem in every field. My friend sets up a depot in Delhi and he needs crystals to put on the frames. So he asks a factory to deliver 5 units of crystals there. Now Shiv is in a hurry to start production, but the factory has its own problems. The factory needs to deliver the crystals to 2 other depots, of course at minimum cost. Let's see how he formulates his linear programming problem. In fact, a factory is located at Chandigarh and Chennai. From these locations, the crystals are delivered to the depots situated at Delhi, where Shiv's factory is, to Mumbai and to Kolkata. The weekly requirements of the depots are 5, 5 and 4 units of crystals respectively. The production capacity of the factories at Chandigarh and Chennai are 8 and 6 units. The cost of transportation per unit is given in hundreds of rupees. Now listen carefully. How many units should be transported from each factory to each depot in order to maintain minimum transportation cost? Let the factory at Chandigarh transport X units of crystals to the depot at Delhi and Y units to the depot at Mumbai. So 8 minus X minus Y units will necessarily be transported to the depot at Kolkata. The mathematical model to the LPP is as follows. Minimize Z is equal to X minus 7Y plus 190 subject to X plus Y less than or equal to 8, X plus Y greater than or equal to 4, X and Y both less than or equal to 5 and X and Y both non-negative. To solve this LPP graphically, what do we need to do? We first convert the inequalities into equations and then draw the graphs of each of the equations to the corresponding lines. Remember, it's only the equality part of the inequality. Now, since there are non-negative constraints on X and Y, the feasible region will be in the first quadrant. The inequality X plus Y less than or equal to 8 represents the half plane containing the origin. The inequality X plus Y greater than or equal to 4 represents a half plane that does not contain the origin and therefore it's away from the origin. Marking the region for X less than or equal to 5 and Y less than or equal to 5, we get the shaded feasible region as you can see. The coordinates of the corner points of the feasible region are A2 given by 40, A3 given by 50, P given by 53, Q given by 35, B3 given by 05 and B2 given by 04. These points have been obtained by solving the corresponding intersecting lines simultaneously. The values of the objective functions at these points are given in the following table. Clearly, we can see that Z is the minimum at X is equal to 0 and Y is equal to 5. And this minimum value of the objective function is 155, 100 rupees of course, or rupees 15,500. Thus, the optimal transportation strategy would be to deliver 0, 5 and 3 units from the factory at Chandigarh and 5, 0 and 1 units from the factory at Chennai to the depots at Delhi, Mumbai and Kolkata respectively. The minimum transportation cost in this case is rupees 15,500, and with that Shiv can breathe easily and take the next step. Now that was some pretty simple stuff, wasn't it? But it seems one of our friends has a doubt. Let's hear it out.
Hi sir, my name is Rawat. Though we have seen how linear programming problem is helping in every field solving their problems, but how does linear programming problem help your friend Shiv in setting up manufacturing unit?
That was insightful. Thank you very much. I was about to come to that. But I've had a change of heart. I want you to put yourselves into Shiv's manufacturing shoes and see what you need to do next. Meanwhile, I'll take a short break, and when we come back, I'll tell you how linear programming problems can help you do just that. Stay tuned. All right, everybody, break is over. It's back to business right here on Math with Shankar. Questions and answers are all a part of this game of numbers. Let me remind you that before the break, we had a question from a caller who wanted to know how the framework of linear programming problems will help my friend Shiv in setting up his manufacturing unit. Well, let's see where Shiv has reached. Okay, he's ready for production, but before he starts, he needs to decide how much. Okay, that is the lead to the question which I am going to pose to you. So put on your thinking caps and let's begin. Shiv's facility can produce two kinds of specialty frames, A and B. The combined capacity is 200 frames. Now he makes a profit of rupees 1000 on producing 1 unit of type A frames, and he makes a profit of rupees 600 on producing 1 unit of type B frames. The manufacturing facilities produced at least 20 units of type A frames. Additionally, at least 4 times as many type B frames are produced as that of type A frames. Determine how many units of each frame type must be produced in order to maximize the profits. Also, what is the maximum profit? So how do we tackle this one? I'll tell you something. I was able to help Shiv out, and I'm going to now help you out. After all, that's what I'm here for, right? As always, identifying the variables of an LP problem gets you started. And well begun is half done. Let X be the number of type A frames produced, and let Y be the number of type B frames produced. Maximize Z is equal to 1000X plus 600Y, subject to the constraints X plus Y less than or equal to 200, X greater than or equal to 20, and Y greater than or equal to 4X. Since the number of frames cannot be negative, we have the constraints X greater than or equal to 0, Y greater than or equal to 0. For the solution, we draw the lines representing the equalities in these constraints. We plot the lines X plus Y equal to 200, X equal to 20 and Y equal to 4X on a suitable scale in the first quadrant. And we mark the region of the half plane represented by the inequality. The line X plus Y less than or equal to 200 represents the half plane containing the origin. How is that? 0 plus 0 for the origin is less than 200, which satisfies the inequality. Likewise, X greater than or equal to 20 represents the half plane on the right of the line X is equal to 20, and Y greater than or equal to 4X represents the region between the Y-axis in the first quadrant and the line Y equal to 4X. Taking the common region of intersection, we obtain our feasible region. Next, we apply the corner point method to obtain the optimal solution. The corner points of the feasible region ABC shaded in the diagram are A given by 2080, B given by 40-160 and C given by 20-180. The values of the objective function z at these points are given in the table. From the table, we see that the maximum value of z is 1,36,000 rupees at the point 40-160. Therefore, x is equal to 40, y is equal to 160 is the optimal combination of the given LP. I think that would be a good start for Shiv. He agrees. So he's on his way. How old is all of this theory of LP problems? Want to take a guess? From the Great Pyramids to the concepts of trigonometry, you might know their definitions, but I'll tell you about their origin. The decade 1930s, the year 1939, Russian mathematician Leonid Vitalievich Kantorovich sits hunched over his book working on optimization problems. 1947, George B. Danzig has a eureka moment. He has just developed the simplex method, which is used to solve linear programming. Still 1947, George's colleagues document a noticeable pattern in a series of military problems. This brings him and linear programming problems into the limelight. Today, linear programming is used extensively. For the time being, back to the present. Before we get on to our schedules, let's go in for a quick break. But don't go too far because you have to be right back to face Exam Decoded head on. Hi, you're back on Math with Shankar. We have seen some classic examples of mathematics being applied to solve some concrete problems in the exciting world of business. And that reminds me of the next order of business, which is to test your understanding of what I have discussed in this episode. But before we proceed to Exam Decoded, here's a quick recap. Today we learned how to solve linear programming problems. We went over a few concepts. The feasible region is the set of all points that satisfy all the constraints of the problem. A corner point is any vertex of the feasible region. A feasible region is said to be bounded if it can be enclosed within a circle. The objective function will definitely take on maximum and minimum values if the feasible region is bounded. First up is the rapid fire round. 5 questions will come your way. Tackle them and give yourself 1 mark for every right answer. Let's go. In the LPP, minimize z is equal to 6x plus 10y subject to x greater than or equal to 6, y greater than or equal to 2, 2x plus y greater than or equal to 10, x and y non-negative. The redundant constraints are option A, option B, option C, and option D. That's right. The correct answer is option A, x greater than or equal to 0, y greater than or equal to 0. Here's question 2. A toy firm produces X toys of type A and Y of type B. The demand for toy B is at most half of that for toy A. The corresponding constraint is A, x over 2 less than or equal to y, B, x minus 2y is greater than or equal to 0, C, x less than 2y, and D, 2y minus x is greater than or equal to 0. You got it. It is B, x minus 2y is greater than or equal to 0. Careful about your inequality signs. Here's question 3. The objective function of an LPP is A, a constraint, B, the function to be optimized, C, a relation between the variables, and D, the equation of a line. B is the right answer once again. Here's your next question. True or false? The solution region of the system of linear inequalities is called infeasible region. Well guys, this one is false. Here's your final question. The feasible region formed by the constraints x plus 2y is greater than or equal to 10, 3x plus y is greater than or equal to 15, x is greater than or equal to 0, y is greater than or equal to 0 is unbounded. If you answered true, then let me tell you, that's the correct answer. And that brings us to the end of the rapid fire. Let's check your scores. All 5 correct, you are a high flyer. 3 or 4 correct answers will make you an achiever. But less than 3, you're still at the learning stage and you need to pull up your socks. I'm sure most of you have scored well. And if you want to test your skills any further, just log on to topperlearning.com. This topic tests you on conceptual ability and representational skills. This topic is a part of the unit Linear Programming, which is worth 6 marks in the exam according to the CBSE marking scheme. And to optimize the chances on getting a full 6 marks, here are the steps you need to show. The question says, in order to ensure optimal health and thus accurate test results, a dog breeder needs to feed his dogs a daily diet containing a minimum of 24 grams of fat, 36 grams of carbohydrates and 4 grams of protein. but the dog should be fed no more than 5 kilograms of food a day. Rather than to order dog food that is custom blended, it is cheaper to order food X and food Y and blend them for an optimal mix. Food X contains 8 grams of fat, 12 grams of carbohydrates and 2 grams of protein per kilo and costs rupees 40 per kilo. Food Y contains 12 grams of fat, 12 grams of carbohydrates and 1 gram of protein per kilo at a cost of rupees 60 per kg. What is the optimal blend? This question is for 6 marks. First, identify the variables from the information carefully. Let X stand for the number of kilos of food X and Y stand for the number of kilos of food Y that are used in this blend. The cost of this blend would then be 40X plus 60Y. We first write down the non-negativity conditions as they are obvious. We have X greater than or equal to 0 and Y greater than or equal to 0. The other constraints come from the grams of fat, carbohydrates and protein per kilogram. We get a constraint on fat as 8x plus 12y greater than or equal to 24. A constraint on carbohydrates, 12x plus 12y greater than or equal to 36. A constraint on proteins, 2x plus 1y greater than or equal to 4. Also, the maximum weight of the food to be given is 5 kilograms. Therefore, x plus y is less than or equal to 5. The optimal solution will be to minimize the cost function c given by 40x plus 60y. And for these steps, you get 2 marks. Now let's solve this system of equations graphically. We carefully plot the constraints one by one. The non-negativity constraints represent the first quadrant. The other constraints carve out a feasible region as shown in the diagram. Be careful, a correct diagram itself is worth 2 marks. By the corner point theorem, the minimum cost will be at one of the corners of this feasible region. Observe that these corners are at 0, 4, 0, 5, 3, 0, 5, 0 and 1, 2. You can notice that we will strike a minimum cost at the corner point 3, 0. Therefore, the minimum cost of the feed for a dog is rupees 120 per daily serving, using 3 kilograms of food X only. And with that, you get your final mark. We come to the end of Exam Decoded. Matthew Klein once said, for every one profitable trading system that is discovered through backtesting and optimization, there are 9 others that lose money. Well, when you have absorbed all that we have covered in this episode, it is that one profitable system that you will have created. I have full trust in that. Goodbye.